Good evening and welcome to this Saturday webinar series by IITACB. And we have seen many interesting webinars in the past couple of weeks and months. And today's webinar series is on AI for science and engineering. This is a very interesting topic. So before I introduce the speaker, let me share a very interesting news at the backdrop. So Government of Karnataka has planned to set up an AI Center of Excellence in AI at IIT ACB. So this webinar is also very timely. And today's speaker is Trapti Kalra, who is AI tech leader, Quantum Ambassador, distinguished data scientist, IBM. And the moderator is my colleague, Professor Sai Gautam Gopalakrishnan from Indian Institute of Science, Bangalore. So over to you, Trapti.
Trapti, you're muted.
Hi, good evening, everybody. We'll just get started. Thanks for that. Okay, so today we are going to be talking about AI for science and engineering. And in particular, we'll focus on some of the new and emerging areas where AI is being applied, such as material science, life sciences, biology, chemistry. With more focus on them, though whatever I discuss equally applies to any kind of area. The most critical thing with science and with engineering is that we have to think about how does it get applied to R&D and how does it get applied to engineering, as in improving the process or optimizing the processes. So a lot of the examples that we will be talking about will be applying to these modalities. So what is, if I just look at the material science and chemistry, what is a typical R&D pipeline? So basically, it is composed of two things which apply to both industry and academia. So one is about our focus on invention, and the other one is about commercialization. And as we all know right now, there's a lot of focus on how, apart from doing execution and engineering, India can also emerge more on the invention quotient. So that is a lot of focus from the government, from different institutions, and we know as our economy is emerging, that becomes very critical. And hence, talent in this area is also very critical. And then the question becomes, how do we really augment the talent here? So if you look at a typical traditional R&D invention process, then let's get aligned on the terminology. So basically it starts with an idea. An idea is generated and we may be looking at different candidate materials or chemistries and to solve a particular problem. And from all these candidate materials which have the required properties that meet up the invention goals, we may have to prioritize and then do some testing. And the testing will call out what are the false positives that we, because of our wrong assumptions or because of wrong data, we have, and accordingly we go ahead and we will again repeat testing in laboratories or through different kind of computational methods till the time we come up with some kind of materials. Now, a viable material will lead to, of course, something like a patent filing process. It could also lead to some kind of an additive which can help in improving a product prototype of an existing product, or it could result in an entirely new product altogether. But once we have a prototype, what are the next phases around it? You need to start with the commercializing aspect, because what is the benefit of an invention if it cannot be leveraged in society? So then it's about development and scaling to come up with a finalized process. And that this itself demands us to, see how we can bring a product to in production, commercialize it at scale. Because many times what happens in the lab is at a very small scale, but when you really expand it to a large scale, you need to really look at what kind of equipment do you use, what kind of operating procedures are put in place. So scaling is another challenge, and it's as good as figuring out the right process, getting everything all together to really be able to make it into a viable product such that can be released in the market. And this process of commercializing applies both whether you're improving a product or whether we want to come up with an entirely new product. So with this understanding of, we can look at actually what is it, where is it that we can leverage AI in this entire process of R&D to commercialization. And if we look at it, it's actually just a small sample of what a material discovery with AI looks like. As I said, we first, at each and every phase, actually, in each and every process step, you can see how AI can augment the entire process. One is to simulate compounds. So there are different tools. For example, for material discovery, DeepMind launched a product called Gnome, which is a big AI deep learning method based on graph neural networks, which helps in simulating stable molecules and compounds. So that could be one, but there are many other kind of examples that we'll see. So you simulate your compounds and you train a machine learning model to explore these compounds, the entire patterns and the properties of these molecules. And once they are explored, it really, again, we can leverage ML or machine learning models to screen them, because the numbers that we're talking about here are in millions. So how do you really go about screening it? And humanly, it is not possible. So then we get into seeing whether machine learning can help us screen the process. And that helps us uh, come to a more manageable search space, which then allows us to pick and choose the samples we would really want to synthesize in the laboratory and observe the characterization and then see what we can do to develop the product which we have in mind. Now, this synthesizing is also something which is aided by AI. We can do a robotic synthesis in a closed lab. This is again a opportunity area. And with that, we can go through algorithmically understanding and simulating the characterization with the observations which are made, maybe with the help of IoT, and come up with our device design. Now, this is a recursive process because as we are learning about the different synthesis we are doing in different trials, we are also trying to understand, okay, what are the predicted properties? And even the success and the failure, the data for all is important in this case because that informs the experimental design and helps us refine our synthesis procedures. Once that is done, then this is where the aid comes ultimately till the time we hit the market. Again, in the process optimization phase, again, we can leverage machine learning. So this is just, like just showing what are all the opportunities in this area. So what are the methods? But when we say we can apply AI, what do we really mean? So traditionally, we have been using in some shape and form some rudimentary algorithms to augment research. So for example, since many years, especially in the 1990s, we were using a lot of statistical analytical tools such as descriptive statistics, hypothesis testing, regression analysis. So these are not new methods. On small scale of data sets, these have always been used and every lab would be using it, especially like in all our engineering programs, in the PhD programs, master's programs. Typically, these are the basic tools that we use. Now, these methods can work well on structured data and on numerical data sets, which are typically collected from experiments and surveys. And they help us in coming up with different use cases, like whether it's around quality control or experimental design. Now, if we move on and we talk about larger data sets, we can explore the space of classical machine learning, which is again not new. We have ready-made packages and toolkits which help us explore and automate a lot of this generation. So for example, we have regression and classification are the two key methods which work on numerical or categorical and numerical data, and they help us in property prediction, material classification, etc. And then if we look at the more broader scope of data, whether it's structured and unstructured data, then we can talk about advanced analytics where we have methods like clustering, anomaly detection, time series, and so on and so forth. And then there are certain, data modalities on which these methods work better and certain use cases on which they fit very well. Now, the emergent you can say algorithms would be around deep learning, and then large language models is something which we can use, which works very well with textual data such as research papers, patents, chemical databases. If you really want to explore them well, then we can talk about graphical neural networks. We can talk about knowledge graphs, as these kind of modeling approaches have come into picture. This is where the data is of much bigger scale, as well as we want to do some kind of analysis which was not possible with the traditional methods, such as really trying to review research papers to find out meaningful insights which were not listed in a database, or extracting knowledge from patent reviews and papers. And then the latest emergent capability that we talk about is agents. So agents is all about bringing some more decision making capability within the agent based on some memory and knowledge which it has acquired, and also some tools which it has been supported with. These tools could be like something like calling another uh, automated algorithm, or it could be about generating PDFs and different kind of documents using a template. It could be something like simply performing a complex calculation. It could also be something where you need to go to a web resource and collect information on a certain project, which is doing a search similar automatically based on some keywords. So all these become tools for an agent, where the agency of deciding when to use which tool is actually with an agent. And that is where we seem to be going in that direction. And you would have heard the term coined agentic AI, which is very popular, which is, you can say, a more matured method, which builds on a lot of the methods which we have listed here. So very simple, just to take an application to give some perspective on what an application could be. This is some work which I did on biopolymer designs. So basically, just to illustrate, I brought it out from the paper to say that, okay, if we had to, how does it actually happen? You're talking about material data and chemistry data. How does it really apply? And how do you really use that to train a model? So for example, I can just give you, let's say there is a database, there's a polyinfo database, which is quite well known. And it has in itself different chemical structures and the properties of these polymer structures all represented. And for representing digitally in the computer, we use a SMILES notation for these inorganic compounds. So this is an example of a SMILE structure. So once we have this, we can actually define a kind of mapping, a dictionary, to encode each and every symbol of the SMILES in a digital format. And this process is called tokenizing. Once you tokenize it, we have actually a SMILES encoded vector, which then becomes a digital input into a machine learning algorithm, such as here I'm showing a recurrent neural network, but it could be any other deep learning algorithm. And using this, since we had in the database, we had all the properties listed against each and every SMILE, we have a very structured data set with us digitally, on which the neural network can learn. Now, how do we really build these data sets? So if you look at overall the big picture, so you could use computational data from past experiments and simulations done, experimental data and databases which are already available, to kind of come up with a data set on which you can train a foundational model. Now, there are different techniques. One could be you take an existing model and fine tune a model with your data set so that it becomes more refined to work with certain kind of molecular structures. We could also train a model to do property prediction or just a replacement, or just a experiment to say, are there replacement molecules available which exhibit the similar properties. The other one could be on synthesis of new bioplastics. There could also be a case where we want to come up with altogether new polymer chemistries. Using all of this, now once the model is trained, it can be leveraged for making predictions in the experimental setup in our labs. That could be, property prediction, new designs for bioplastics or new polymers, or coming up with new polymers altogether. Whatever work happens in a lab, what is very important is that that data, whether we are succeeding in certain experiments and research or we are failing, both that data becomes very crucial if well collected for us to refine through the expansion of the entire data set. So we can enrich our data set by just feeding in all the data from these experiments, because this will enable us new ways to explore data. We will learn from the field experiments what does not work or what alternatives can work, maybe in another problem, because you have the historical data. Each and every data has a value and that can be leveraged. And this is a cyclic process. So as this process sets in, and let's just visualize it, there's a certain lab in a institute like one of the IITs, and they have such a platform where they can collect this data, refine, and they could be a faculty such as yourselves here, where you have a research agenda. So think about when PhD students may be coming and going and helping you forward a particular area. Let's say there's a research group which really works around bioplastics or biopolymers. Then they would like the data for the students who may be going out to be leveraged by the incoming students, so that the overall objective of the research does not get lost in papers and textual information. So if we have such a platform which can enable us to do this, that would be a great way to look at how we can start using data and then AI to fulfill and fast track our research. So, so then there are also more different kind of solutions. So I talked an example of a simple neural network, but what many times you'll hear all these different terms around generative AI. So let's just take a look at, what is there for generative AI. And this is from a paper. I've included the archive link here. And it talks about generative AI for material science and what are all the different methods where Gen AI can help. And why focus on generative AI? Because one was about understanding the data as is, to be able to predict properties or things which are difficult to us. How do we discover them? But when we talk about generative AI, it's important to say this is net new generation. So net new generation of new molecules, new structures, or new properties. So how does that come about? And there are very in the last I would say 20 years, there's been a lot of research around coming up with generative AI techniques. So one of them is the auto encoders. Here, what happens is basically you learn from an existing data set by encoding and bringing the entire information in a lower latent space, and then you use it with some noise through a decoder. You teach it how to come up with the same matching um, output which matches the input, and through this process the decoder actually gets trained such that they can start generating and show emergent behaviors where they are capable, with some perturbation, they're capable of predicting new kind of properties. So this is where when you would typically want to explore molecular structures or do some kind of similarity search, so such a model could be used. Another popular algorithm is GANs, or Generative Adversarial Network. Here we actually have two neural networks. One is a generator, which is generating a lot of synthetic samples, and a discriminator's job is to actually try and recognize these synthetic samples. And on the basis of that, it's able to, both of them get better at their work. And then once we stop the training process, this entire setup of neural networks, both of them together become very good at coming up with new kind of realistic outcomes. They can predict net new outcomes. And this is used for generating new molecular structures. Similarly, reinforcement learning is another paradigm. Here, actually, we train an agent to take some actions in an environment, and with such an objective function that the agent is rewarded, where the cumulative reward for the actions that he's taking is going to be higher. So the agent is therefore trained to take better actions. So it's another kind of very different from the traditional deep learning network. But here, this could be something which is used for optimizing process outcomes, or it could be also used for just exploring reaction pathways, since we're talking about molecular material science. So how can you, when chemical reactions are happening, what could be the pathways that can happen when we change different conditions or taking different actions? That's one paradigm which can be explored well by reinforcement learning. The other one is around flow models. Flow models is a little bit similar to the encoder decoder. Here we basically take an objective function which we call flow. We kind of apply some kind of transforms to it, and then we try to reverse that function to get the same output. So kind of it is in the same lines, and this is also used for sampling through complex distributions. And now the other one which we know is the transformer based architecture, so which is the architecture behind large language models such as ChatGPT. This can also be applied to chemical structures, where we talk about again some kind of sequence, because text is a sequence. Similarly, a chemical structure is a sequence, and a chemical reaction is also a sequence. So applying them for reaction prediction and property estimation is another emerging area. The problem with all these models, and this is again something which is out there in research still, is that often because our data may still be limited, some of these models are really huge, like they have a lot of capacity to observe information. They may end up memorizing the data set, and that is one mistake we need to avoid if we really want to leverage them for generative capabilities. So that is one problem. And then the other problem is what they're really learning at the end of the day are patterns. So what they do not really understand is the core principles around material science and chemical principles of science. That is an understanding they do not have. So that how can we imbibe them with this knowledge using symbolic AI or any other kind of methods is an open research area, where if anybody is interested in exploring it, it's a great place to get in, because this is something which I think will help us come up with better capabilities in the generative AI space. So, so another example, since we talked about the LLMs, I wanted to again, came across this very interesting paper which I want to discuss with you. So it's really about multi-agent reasoning systems. So we talked about, okay, there are some traditional methods. Then we also looked at, how we can use generative AI for applying them to the area of material science and chemistry. The one area where a lot of researchers would typically spend their time is coming up with the whole research mindset, where you are coming up with an idea, you're looking at your experimental results, you're trying to come up with uh, comparisons, you're trying to analyze the design principles behind your problem, and then you're coming up with some kind of review process where your peers or your supervisor may be reviewing the work, such that you can forward, you can come back and take feedback and then again refine, maybe do more experiments. So this is an ongoing journey, and this is where the human intellect is getting leveraged the most. So you may be using a lot of other tools, but this whole process of where you are reviewing, deeply thinking about a problem, getting it criticized, then from that feedback, learning and improving, this is a cyclic process. And typically, this is how we work when we are doing a PhD or we are writing our own thesis. So what this paper tries to do is they try to see, okay, can we leverage an agentic system which is powered by a large language model and it has some personality of its own? Can we leverage it to actually help us in coming up with net new research independently? And the idea is to leverage graph neural networks in this particular paper. So what it really does is, first of all, we take a lot of literature and we try to come up with a graph neural network with past papers in a certain domain. And that this what we show here in the top picture. This is the global knowledge graph of a particular topic. And then we have an agent which defines a role as an ontologist. An ontologist is somebody who can understand graphical knowledge in a good way. So this is a person who or an agent who will actually focus on understanding for a particular given objective what all are the paths it can take through the knowledge graph and define all these paths with their terms and what are the connections and interconnections between these different paths. So kind of coming up with related knowledge, something that a human would do when they are researching through all the papers and collecting all the literature for further refining their problem statement, or if they already have a problem statement, just collecting information around that problem statement. And then think of again a agent who's playing the role of a scientist, where based on this finding from the ontologist agent, this agent will actually craft a detailed research proposal, actually write it out based on different key components. In this paper, they have focused on coming up with the hypothesis, the outcome, mechanisms, design principles, what are the unexpected properties, comparison, and novelty. And there's some way of objectively measuring novelty coming out of this research. Now, this is just a draft at a high level, but there will be another agent called scientist 2, and their job is for each and every of the high level analysis done, breaking up and going into the tasks sequentially one by one and gathering more information or detailing out in a better manner. And here, just expanding on one specific concept, but going in full detail and critically assess what the scientist one has done. And that's how we prompt or we would expect the agent to do and provide him with the right tools. And the knowledge graph is, of course, accessible to the entire, you can say, party of agents here. Finally, a critic provides a summary of the research idea, conducts a thorough research, and highlights the strengths and weaknesses in the research, what are the alternative improvements that can be done, and gives that kind of idea. So in a way, that process of, let's say, about 2 months or 3 months of initial research can be done, and we can get some good insights leveraging the knowledge graph, which has been actually, it has the knowledge of all the literature that you could assemble to impart to this particular knowledge graph. So this is one, you can say, a standard pattern which you can follow. The other pattern is that we just let loose a lot of these different agents, which includes a planner for coordinating the action, that which agent should be called after which agent. So kind of in any manner. So it is more randomized. And all these parties in any random manner can actually, with some objective function in mind, you can see that, okay, how can they all work? Plus, we can also have a human review step in between where they're looking at the work from any one of the agents and then adding their own direction to it. So such a system is something we'll actually see how we can bring this to life, after a small break, because I know we've discussed it. So this is, we are more or less towards the end, and then we'll have a break for Q&A. So this is another pattern where, you bring a lot of different agents together and they coordinate in a randomized manner to come up with a outcome. So if we just have to look at the entire process, what is actually happening here? We are subsampling a subgraph from the overall knowledge graph pertaining to a problem, term, molecule, desired property, something we are defining such that we can search and get a list of definition of concepts and relationships. And then in a hierarchical manner, we are going to different steps through the research, refining and expanding on these, and finally coming up with an integrated draft proposal for our research. So this is what the paper talks about and explains how we could actually do reasoning and analysis and planning on a research topic, leveraging data and how it compares to human effort in doing the same thing. So this is something you may want to do, to look at. And before I leave, I just want to highlight one thing. Since the advent of deep neural networks, that was, I think, the seminal papers came out in 2014. What we have seen is there has been impact, as I explained, all the methods on the field of material science, and there has been a cumulative increase in depth of both like the syllabus and what people are learning in material science, as well as the kind of publications that we are getting. So it is starting to be exponential growth. And what we have also seen is, in a in 2024, in 2023 and 2024, there was for a commercial enterprise where they were doing R&D work in the healthcare, optics, and industrial manufacturing space. There was actually a trial designed, and this trial was all about assessing the impact of AI on material science domain. So really to understand that, okay, what impact does AI have when we provide AI tools to material scientists working in an organization on R&D, what happens? So what was actually done was an LLM-based solution, such that I described in the earlier slide. This tool was developed and it was handed over to the 1,018 scientists of this research group. And there were 3 trials done, again with random scientists partaking in each trial across multiple months. And the idea was to see that, okay, there was a there was a control group which had access to this ML tool. They were provided training on the tool, and there was another scientist group which did not have access to the tool, and they continue to do their work, one who had access to the tool and one who didn't have access to the tool. And what they found was the group which ended up with having the AI tool at their disposal, they were able to identify 44% more materials, and these were stable, valid materials. They were able to increase almost 39% in patent filings. And in the product prototypes, there was a 17% rise. Like these are net new compounds, because there's one observation that as we start using AI, there are also a lot of false positives, because you try to prompt much more ideas, like more ideas come at your hand. So there are also a lot of false positives. So you also end up having to deal with them and use your judgment to handle those false positives. So that's an observation, but this is something which has been published as a finding. And the other impact of it, while AI can probably aid the R&D, there is a impact. The impact is on the job satisfaction. So that is what the key interesting outcome came out from this, was that there was a change in satisfaction. So while the scientists were happy with the productivity that they were seeing, increased productivity in getting through the initial, you can say, laborious tasks of R&D, they did see they were not very happy with the net happiness was lowered. And what was the reason for being less satisfied with their job? One was they felt that they were underutilized, their skills were underutilized, their work was becoming less creative and more repetitive, and they didn't feel as much credited for the work they were doing. And also there was some complexity in dealing with the AI tool. And there's one scientist who said that while I was impressed by the performance of the tool, I couldn't help feeling that much of my education is now worthless. This is not what I was trained to do. So that was like one of the statements made by the scientists. So I thought this is a very, interesting aspect, or a societal aspect of AI in general. And I just thought it will be interesting to share with everybody. With this, we can have a small break in case there are any questions, and then I'll be showing a demo of one such capability.
All right. So thanks, Trapti, for the nice talk covering the sort of different use cases for AI. You specifically mentioned biopolymers, a little bit on material science, and also on using agents, right, to develop research proposals and so on. And also touching upon the final topics on the impact of AI on research tasks, and also job satisfaction, right? So I think there are already a couple of questions from the audience, but before I sort of take them, I would also like to encourage the audience to post more of their questions. We'll try to address as many as possible in this break. And if we are not able to get through all the questions, we will get them at the end of the talk. I'll start with a couple of my own questions, and then I'll start with the audience questions. And both of my questions are towards the second half of your talk. I also had questions at the beginning, but I probably pushed them towards the end of your talk. So one thing that you showed with the impact of AI on the science tasks was actually a reduction in the ideation time and an increase in the judgment time, right? So that was in the middle graph that you showed. Would you consider a good thing or a bad thing?
Yeah, so it's a mixed baggage right now. It's a good thing because if you're increasing your judgment time, that means that a lot more ideas that are being given to you automatically, which you now need to use your human judgment and experience to evaluate. So that's why there's an increase in the judgment time. And the downside is that, you are actually wasting time, which you may think you may have spent in ideating or in actually taking the things to market. You have to critically use your critical judgment to do so much more evaluation and remove those false judgments. And again, that is where the question becomes, maybe that's another opportunity for AI where you can help it come up with less false positives. So that's always a machine learning problem. How do you reduce your false positives is always what we try to address. So what this research actually showed us was, yes, there were a lot of false positives as well, and therefore the need for experience of the scientist is still there, very much there, because they are the ones who are judging it.
No, because intuitively, I would expect the experimentation time to go down. And as a scientist, the thing that almost always excites me is the creation of ideas. Right? I would like to create ideas, or I would like my students to create ideas, rather than a machine feeding ideas. I mean, I also appreciate that. But ideation is where I think the scientists really like their role, and of course, judgment and experimentation is where they would like to reduce the load as much as possible. So that was very interesting to observe. The second thing I wanted to ask, once again, that's on the impact of AI, was when you said that the job satisfaction, right? So although the productivity increased, the sort of satisfaction sort of dropped a little bit with AI. Does it have to do with the intrinsic human need to feel like you have contributed something? Because if you think about most of our work, right? So we have the sort of creative, productive pieces of our work, and we also have the redundant pieces of our work. But the redundant pieces, once are easier to complete, and whenever we complete them, we feel a sense of satisfaction and we feel that we are contributing. And maybe AI sort of removes that, and hence people feel lost. Is that a contributing factor?
Yes, that is, of course, a contributing factor, because what was done is, what is a direct factor is, if you learn something, you want to apply your skills. When you apply skills that you have learned, that is a source of satisfaction to us. And that is how people in different professions are always happy. That's why you would also be happy if you learned how to cook and you cook a good meal, you will be happy. But now that very skills, if you learned, if an AI is able to accomplish that, and now they are hitting R&D, which was earlier like something which machines will take a long time to get, but now they're hitting it. So that becomes something which is directly impacting people who are creative by nature. They are getting a lot of other ideas which people would have appreciated and paid them for. Today, you can actually go and generate images, creative images. So all these creative, jobs, tasks, skills, they may feel like threatened. It is an opportunity and it is a threat, I would say, and that's what is also reflected here.
Okay. So we'll take a couple of questions from the audience. I think we'll move the rest to the end of the talk. The first question is, could you please comment on popular computational representation of polymeric molecules for ML workflows? So for example, are smiles good enough for polymers as they were originally developed for modeling small molecules?
Yes, so smiles is for small molecules, and then there is selfies, which is another. So there's actually a model in IBM which we've developed on selfie strings, and the selfie strings are what actually are meant for polymers, which are your large molecules. So if you train now using the syntax of the selfies, you can actually train models for large molecules as well. And then we'll be reviewing another paper, the GNOME paper. We'll look at the architecture and how we solve large molecule problems as well in inorganic space.
Okay, thanks. Thanks for that. The final question for this break is, how do AI multi-agent systems avoid conflicts during collaboration?
Okay, so again, this is something I will cover in detail. I'll show you how to design a cognitive architecture for a multi-agent framework where you are managing a lot of reasoning, planning, memory, different types of memory to actually enable agents to kind of think cognitively the way humans do. And the way in a human society we encounter conflicts and we both work in collaboration together. We also have our own conflicts. So we'll see how that interplays here, though a lot of the emotive component is taken away. So the conflict will mainly be your arguments, or you came up with one hypothesis and there's another hypothesis without the emotions coming into picture. So that is both advantage for us, as well as it is more objective how you handle that, because you can always put an objective function when you talk about a decision. So we'll look at some of those patterns as well.
Right. Yeah. Thanks, Trapti. We'll take the remaining questions at the end of your talk.
Okay. So now we'll talk about an emerging capabilities, and one of the emerging capabilities that I want to demonstrate today is a small demo of such a capability, which is being developed by sarthak.ai.com, which is a startup. And I think we have the team also in call here. So it's Satvik and Meghraj and Shantanu. They've developed this product. So most of what I have told you already, and what we'll be talking of, I see this kind of being realized. So I kind of advise them, and we'll see how this is coming up. So you can visit this website, and you can also see some of the cool blogs that have been written. And if you want to join the waitlist for this product, that is also something which you may want to do. So I'm just going to go to the live demonstration of this application. So the platform name is Both Scientific, and it is meant for chemistry and material science domains, but it is not limited to this particular domain. It can work for actually any domain, and I'll show you how. So I'm just going to log into the domain and show you how a project is actually getting managed in this. So in this landing page on the Both Scientific platform, I've logged in and I see my dashboard. So think of it that, I am a organization user, maybe part of one of the research groups in a big institute, or it could be an enterprise or a commercial setup where there's an R&D team. So typically when we need to do R&D, there may be multiple projects which are ongoing. And this is a dashboard or the landing page where you can see all your projects which are in place. Today, we are going to focus on the caustic polymer development for Soundtech. So Soundtech is a company, and we're going to focus on, they're trying to actually improve the polymer development for soundproof polymers, because they're facing some issues that, they don't retain properties. The polymer doesn't retain property, and also there are not uniformity coming in the kind of polymers they design to enable acoustic blocking properly. And if you just navigate here, like I'm just trying to say that this is a really cool tool. So you can maintain your calendars, you can share, you can have a team set up in this to manage the projects within an organization. You can look at plan all your meetings here. You can really quick start to add a team, document, or access certain machine learning models. You can also see what are the recent activities which are happening in this space. So this is the dashboard page from where you can navigate and handle all your work. And the good feature about this tool, and why I was saying it is, actually quite broad in its area of application, is the idea is that any organization can bring their own databases, historical. They can start fresh. I mean, you could start with no database at all. There's no restriction. But you could also bring in all the kind of databases that your organization uses. So here we are looking at raw materials, which is for For this particular sounding tech Inc., they have like multiple databases around calibration sets, equipment, then again equipment which is used for caustic polymers and their raw materials. So they maintain a list of all these equipments and raw materials, etc. And these can be pulled into any project or into any kind of trial and experiment that they're doing. And this is a thing they can automatically organize, they can bring in from other tools, etc. And if I just move on to the projects, so let's talk about one particular project. So we're looking at the acoustic polymer development for sound tech. So here, if we just have to go into the project, okay, I think it's another one. So let's say optimized extrusion. So we're talking about extrusion here. So in optimized extrusion for noise observing project. So within the project, you can conduct multiple experiments. Typically, that's how we work. We'll pick up a project and objective. Within that, you could have multiple experiments. Within each experiment, you will typically be doing a trial, right? And you could do more than one trials within a particular experiment. So what we can see here is for this particular project, we are trying to list down all the experiments here, and we can see what this project is all about. You can enter all the names. We know which is the team which is working on the project, and we can also enter all kind of metadata around the project. You can attach more literature because there is an agent which is getting trained behind the scene on everything that you're bringing in your project. And this agent called Bodhi for the both scientific platform will enable us to actually fast track our research. So, so we bring in the description, and more data the better. How will we manage the budget, the risks and contingencies? So we add all this information here, and we can then start looking at, okay, what kind of trials are actually happening. Now, there is since this is a kind of sample demo project that I'm doing is, so what the team has done is they've come up with a polyquel. So this project team has come up with a polyquel type of acoustic polymer for which they're trying to improve the properties. And for this, they're trying to actually study how can they improve the extrusion throughput such that they get better properties. So for that, they're conducting various trials, and you can see all the trials being listed here. And you can see how this particular experiment is mapped. You can see all the general information for this, what is actually the hypothesis and objective of the experiment, how the experimental steps are happening, what are the associated protocols, what are the associated materials and equipments we need to look at, what are the risks and safety protocols. Now think about all this information, which typically would be done by a couple of masters and PhD students working together along with the professor. Or in an R&D setup, typically you have a technical director who's working with his team of scientists and technicians. All of them have the same visibility on the project. They know exactly in real time what the status is. Plus, we are capturing all the data for this project in this organization. All the data is coming together, which can be leveraged across different experiments and across different projects as well. So using this, we can study in detail. Now, for a particular trial, let's say we want to search through the trial. So within an experiment, there can be multiple trials. So let's just take the example of the polyquel, since we're talking about this compound, how the extrusion under high pressure conditions happens. The other one could be baseline trial, like standard extrusion parameters for polyquel. So what I see is, if we go here, we can actually see all the trial data that is getting entered. So there are some certain measurements, a data set has been found out during the trials, and you can enter all the data dictionary, and you can also see, okay, for this particular trial, what were the observations. And we can also import export data. So we can also do an IoT integration into it. So all your trial data comes together in this way. So you have a project, you have experiments. For each experiment, you can manage all your trial data here. And then the beauty of the tool is that given this trial data, if we want to simulate and create any kind of AI models, we can do that. And you see, this is a place where for this particular organization, there are multiple models that have been prepared, they have been trained, some of them have been deployed, and this is related to everything that SoundTech Inc. company actually does. It's related to their domain, and they leverage these models on and off across different projects. So one such project could be where they're deploying a simple model for actually predicting the extrusion throughput. And that's what the model is. So any team can come and actually use this model. So here, this model, and how is that model trained? What are the key characteristics of the train? Here we see a parity plot for the model. We can also see what is the feature importance. We can understand more insights about it. And these have been done uh, with some effort and some engagement on the collected trial data, and the models are automatically prepared and deployed through the platform. And once you have this kind of a capability, you can actually use that to make any kind of predictions. So this is the prediction happening, and we could also change any kind of parameters and see in real time what kind of predictions are coming out from the model. So like this, along with the project experiments and trials, we are managing the entire data flow, including applying of ML solutions. This model could be a regression model, a classification model, a deep model. Any kind of model can be enabled and included in a project. So again, it depends on how the organization or the institute is set up to do their own research. And then finally, if we move on from the models, if we really go back, the cool part about this is how do we really leverage intelligence? So there is a talk to Bodhi chatbot, which is now behind the scenes learning everything about the project. But it's doing though in a very private context. So the database in which all the data is being saved is very focused on this particular enterprise only. So only people who are aligned to a project get to see and get to see how AI and an agent can actually handle all the information. So for example, if you had to ask the agent to, share the list of all team members for my project, because it has the project context. So it will be able to kind of ideally suggest all the team members who are aligned to this project. So there it goes. It's given us all the correct names. And it can also generate reports on our project. So let's say there is one active experiment which I just took you, which was using the model, right? So if I just say that generate a PDF report for my active experiment, let's see what it does. So it is giving us a complete list of what all is happening. There were 10 trials that we saw, and then it is giving us the detailed information about all these, what are the protocols used, what was the source of information, what were the risks, what kind of attachments have we made. So it is giving us all the data, and we can always like take this PDF and save it with us, look at it. And if we give it a template, I didn't show that functionality, but it can generate a particular PDF in a very fixed template, such that a lot of that work of labor of, bringing all your findings together, sending them off to review can be taken away. Also, your like team members, supervisors, peers can come and review the work. So this is the kind of capability. And if you look at it, actually, what the team is trying to do really bring a lot of intelligence into this entire platform. So when I came across this platform and I thought we have to talk about some subject, how AI applies to science and engineering, I thought that these kind of tools are something which are really great to really bring. And this is not the only thing. So I'll be talking in the second part. I'll talk about a lot of other tools as well. But yes, if you would like to reach out to the team, then do care to visit their website and join the waitlist. So as I mentioned in the earlier part of the talk, how do we really go about designing cognitive agents? So Sai, that was your question, that how do they avoid conflict? How do they collaborate together? So we look at some of that. So the cognitive agents really started first by having the whole idea came about. So we've had AI assistants since long time. but they were very, very, you can say, tactical in what they could do, generally having no decision making ability and no ability to reason or to plan on their own. And that is why they were called an assistant. But now we have agents. So, how do agents evolve and how are they different? So, the first stage is that you have a strong LLM and there is an input and there's an output. And that's what we use when we converse with chatbot, like chat GPT every day, right? That's the simplest form. Now think about the ability of a language agent to take actions uh, in the environment and receive those observations back such that it is becoming smarter, taking the information from the leader. And that's what we saw with the Bodhi Scientific also. What data is being entered on the platform, it is becoming smarter by understanding all that data from the trials, from the kind of model outcomes, from the literature you're bringing it to it. Plus, it has the knowledge of the world from the because it's backed by an LLM. So like this, you really start getting a notion of how capabilities are increasing because it can actually take in observations and it can give improved output by taking some kind of feedback. The third stage is where we really start talking about cognitive agents, which cognitive is actually, if you can say, inspired by the cognitive science methodologies. So here you really talk about now the cognitive language agent is an LLM which has a memory of its own, which means it can maintain some state of what has happened in the past, what was the action, what was the outcome. And there is a capability to use that to reason before giving out a response. If we can bring this embodiment to a computer program, that's when we can see how it can be similar to a human with some kind of cognition. Because ultimately, we use our experience, we use our knowledge, and we use feedback from the real world to take actions, to be informed about any kind of task we need to perform. So so the whole idea is that can we bring that kind of a principle to life? So if you look at it, if you know a bit about cognitive science, you would know that there are different types of memory that we as humans have in our own brains. And the idea is that can we bring these or can we design an architecture where we can also have different kind of modules of memory empowering this particular agent. Procedural memory would typically be similar to the skills we know. For example, we know certain ways of working. These could be coded as in a software program. Then there is large language models which have a lot of information about the world, right? And you can retrieve and you can also train using some kind of memory, working memory, where you are working and taking decisions. So this is procedural memory. Semantic memory will really be just your knowledge bank, like what you learned in school, the basics of science, all the knowledge, all the exams that you give, right? All that becomes part of your semantic memory because it's memorized. So those could be the, different, you can say, domain knowledge. This is what is embodied in semantic memory. Then the third kind of memory is episodic memory, which is really about when what happened. It's about an episode that because you'll always remember, for example, a certain birthday which was celebrated well, even when you were 4 years old, you'll probably have some kind of memory of it. This kind of a memory is typically episodic memory, or you remember the birthdays of all your near and dear ones. So that's an episodic memory. So this kind of a memory is a different kind of memory. So having specialized memory uh, modules from which, based on some kind of reasoning paradigm, the agent can tap into it. It can both learn a memory, decide when to learn a memory, as well as when to retrieve a memory. What is managing, you can say, like the decision making in our brains as well. There's a decision flow, a decision procedure, which is actually managing different kind of interactions. The prompts and parsing of the response from an LLM is one. And then for different kind of agents, retrieving the information as and when required as per the decision procedure is another one. And the decision procedure has to take decisions, and this is powered by a reasoning engine. How this reasoning engine actually works is by both taking in observations from the world, from the external, and or taking some actions, and these actions will again lead to some kind of observations. For example, think about an agent which is a good, you can say, agent which talks. They could be taking some actions, hearing some input from a human, that becomes an observation, and on the basis of that, they can reason. And how reasoning actually works, we can think of reasoning to work in a computer program. I'll just talk about that. But the idea is that there are some actions, observations, uh, which are analyzed in the working memory, which inform the decision procedure, which is more procedural in nature, leveraging all these modules behind the scenes. And this together is what a proposal for a cognitive architecture is. And this is what a tool would typically want to embody to have a very effective agent, right? And if you look at the agent decision cycle, how the memory, working memory and decision work together, then it's really about looking at an observation from the world, then coming up with different proposals by tapping into the past memories. Given this observation, what are the related similarity actions that were taken? What memory, what kind of outcomes can we look at? Then how to evaluate them, select them, and based on one particular selection, you go and execute them again, and that forms the full planning phase. So this is a agent decision cycle, and this agent decision cycle actually results in some actions being taken. So reasoning and retrieval are the internal mechanisms which help in planning, and learning and grounding. Grounding is external. All the data that you're getting grounded from the external world, right? And that and learning, they all work together as an agent action space within which the agent acts. So this is a kind of cognitive architecture which can, and there is been again this paper which talks about potential ways of implementing such an architecture and discussing more on the different patterns around this kind of an architecture to result into more intelligence. So, so with this, if you look at what are the current state capabilities, I think I have very few minutes. I'll just try to close it soon. So one is DeepMind has uh, a very good deep learning graph network based method for material exploration. And there is a blog which I think if everybody in the science stream should actually visit this. What they really do is they have come up with a graphical neural network structured pipeline for evaluating multiple candidates, and then experimentally validating these experiments using DFT computational methods. And only the validated molecules which are found to be stable have been put into the GNOME database. And as of now, there are 4.2 lakh molecules, which is much above the discovered and already known space of about 20,000. So through human experiments, there was a limit to how much stable molecules, inorganic compounds we could actually come across, and that number was around 20,000. But what GNOME did was it expanded. Now, with the traditional computational methods, like there's a project called the Open Material Project. There are different other kind of computational projects which are there in open source. Using all of that, the number which could increase from human experimentation increased, actually doubled, more than doubled here. But if you look at the capability of GNOME and what it can explore and what it has explored to be stable compounds, net new compounds in the world, that is a huge number. So you can now start to see what is the benefit of just having these generative AI concepts out there in the world. The second one is AlphaFold. I think this is very popular. Most of you will know. This is actually an area where using deep learning, the whole science of biology is transforming. When I say transforming as in terms of research and discovery potential, and what they really have given to us as to leverage is the AlphaFold protein structure database, which has more than 200 million protein structure predictions, and they can support research. They also have this server out which is accessible to everybody in the world, where if we want to see the model interactions between different structures composed of proteins, DNA, RNA, ligands, you can do that. Just you need to make a server call and register for the service. And the good thing is AlphaFold 3, which is the latest version of the model, that is actually the model code and weights have been open sourced for academic use. So again, this is a great area where it can be leveraged by scientists. There are also some good closed source tools apart from what DeepMind has. So one is NVIDIA Clara. This helps us in, genomics. It helps us in drug discovery. It also helps in coming up with models for patient monitoring care, using how you can observe a patient and all the important monitoring parameters, and do an automatic care of the patient and automatically give alerts. So that kind of thing, and of course help in coming up with structure, how to analyze using different imaging techniques, 3D imaging techniques, the internals of the human body. So this is a great platform from NVIDIA. Citrine Informatics is another company that has a AI-driven product similar to what both scientists has for development software for materials and chemicals. And then Benevolent AI is another one. What they have done is they have brought in 85 plus data sources across different kind of omics, patient literature, regulatory documents, molecules, biological. They brought together all the data and they make that available in a well curated and accessible way through their whole. And they have different tools for data visualization, for data research, and then finally for modeling. So this is another, great place which to explore. While these are closed source tools, there are also plenty of open source tools. So I've included some. One is the materials project, which is very popular. There is also a project by IBM. You can check out the IBM GitHub materials. And this is actually the foundational models for materials architecture, which IBM is working on. So what IBM is doing, they're coming up with models, algorithms, functions, and they're trying to train different models on different modalities. Like I mentioned about selfies for the large polymers, and smiles would be for the smaller molecules. Then graph models, 3D positional, electronic density. They're bringing all of this together in different models and fusing them together to enable powerful downstream tasks, such as either making predictions using these different molecular structures, or even doing some kind of cross-model inferencing. So that's something, and slowly they are adding more and more models here. And in the material project also, there's been a lot of, you can say, progress on different kind of databases that have been created. So starting with crystal structures to molecules, band structures, each of these properties help us understand something different about the molecular properties, whether it's related to their absorption rates, or their elastic, dielectric, or electrical properties. So this is another way in which you can visualize how the materials project is also leveraging machine learning to improve the kind of data sets they can deliver to everybody. And a very interesting project is the Open Materials, which is actually backed by Meta. So Meta has a group called the FairChem. And if you know that Facebook or Meta has actually come up with their own Ray-Ban glasses, and what they were actually trying to see is design better polymer materials for having a very good experience with their glasses, and which can also meet the needs of supporting, look good and have a lot of intelligence to be embodied within the glasses. And they have discovered new materials and open sourced actually a lot of their models and their process of how they've done. Again, a very good place to go and see what is happening on the open science. And finally, my last, I'll just like to end is what is our considerations for future. So basically, we need support for innovation. So startups and the students, academia, everybody needs support for leveraging some of these tools, coming up with their own innovation, how to bring AI and different sciences together is something that we need to work towards. And again, education and talent readiness is another thing we need to think about. How do we make talent ready to leverage these kind of tools, and just the changing expectation of how the future generations will be working in these areas. There are some challenges as well around data diversity, denoising, synthetic data generation, how to do them best, how to trust these items, and how to really have algorithms which can work in science areas. So these are all open questions, open projects, you can say, on which you can do a complete research. And then how to bridge cognitive science and AI, further research needed. We just saw one example of cognitive architectures, but yes, there is a lot of room here to bring cool solutions out where agents become smarter and smarter. Then there is an opportunity to design closed loop labs with IoT integration so that even the process of experimentation can be automated to some extent. Then there is a need for a lot of open data and model repositories, more than what the big tech is already doing for us. What else can be done? And finally, while academia may also adopt it to some extent, we need to look at how industry can adopt these emergent technologies and really enable a lot of corporates to also have come up with better R&D institutionalizing. So I don't think there's a lot of scope within India for us to have our corporates also back research better and also do their own research much more effectively. So with this, I'll just end the session and open for any questions.
Okay, so thanks, Trapti, again for the very nice talk, for the demo of both scientific interface, and also touching upon many of the materials models, as well as databases that are out there, and also touching upon some of the challenges. So once again, I'll start with some of my questions, a couple of my questions, and then I'll take the audience questions. There are a few of them from the audience as well. So going back to the earlier part of your slides, you made a very important point that often, if you look at generative models, right, they end up memorizing the data that you feed in, and instead of sort of creating correlations, so to speak, right? So they are not truly learning in that sense, and you emphasize the need for introducing some kind of chemical or chemistry constraints or knowledge within your models. So in your visualization or imagination, how would those constraints look like? Because these are very different from sort of physics-informed neural networks, right? So where you can introduce some kind of additional loss functions that take actual physics into account.
Yes.
But here, chemistry is more of a science of exceptions rather than rules. So how do you visualize encoding those exceptions?
Right. So that's an open question. One thing could be to bring in more different kind of like what we are trying to do at IBM is we are trying to look at different model architectures. Can you leverage graphical neural networks and deep learning networks together? Because both of them exploring chemistry in different, you can say, dimensionality spaces altogether. And then we are fusing them together, So we are bringing, you can say, a mixture of experts from different areas. So that is one technique. And again, that is a computational technique. The other area is there's a whole emerging area of neurosymbiotic AI, which talks about how do you empower machines to learn about symbols, the meaning of symbols, how symbols can work together. So that's another area where some of those ideas can be brought in. And then how can you leverage textual literature and different data modalities, time series data? Like there is so much of opportunity to explore it, but it is not a solved problem. And this is exactly where, it is an open concern that how do you bring that knowledge in? But yes, at a smallest scale, again, with a lot of training or preceding, some learning can be done, but how do you do it at scale and how do you do it broadly? If you see what has happened in AlphaFold 3, I think that is what will happen in the material science space as well. Because they started with AlphaFold 1, which could just understand and predict the protein structure. Then they then they matured that model to start working with other compounds and being able to predict reactions, right? So there is some learning inherently happening where the model is not collapsing. So we have to keep experimenting and see how that whole space evolves.
Yeah, my second question was going to be related to AlphaFold. So if you look at AlphaFold, right, so that has basically solved the protein folding problem, but and it's been given the Nobel Prize and so on, right? So in material science, we don't have such models, right? So even if you look at the state-of-the-art generative models like genome or MatterGen and so on, they are not particularly good at generating, let's say, chemically reasonable structures. They often generate structures that do not obey sort of bonding rules, they don't have an intuitive collection of elements within that. So how do we? I mean, is there a pathway to generate the equivalent of AlphaFold 3 for genome?
Yes, so yes, again, it's open research. Genome is actually right now state of art from a very broad-based perspective. There are some particular narrow domain. Again, you'll find some powerful models. There's another model for polymers by Khazana. Then there could be your own research lab which is producing a lot of data. You're focused on a particular problem. So in that narrow area, you may achieve some kind of a breakthrough. But that problem of the general inorganic compound understanding, extraction, reaction, prediction, and property prediction problem still remains. But then I would say there's a lot of work happening. So the other thing I had touched upon is where I would encourage everybody to look and contribute will be this AI Alliance for Materials and Chemistry. This is a very specific group. And I think for AI Alliance, IIT Jodhpur, IIT Madras, and there's one more IIT, they're already part of it. So the whole idea here is work together, and IBM is also part of it, work together to come up with different kind of modalities and explore this very specific problem. What kind of architectures, if not this kind of a paradigm, or what Equiformer is a model by Meta, which is doing research in polymer space. So if not these kind of models, what are the kind of models? What modalities are we missing? What are the drawbacks of this kind of, and you can actually go through this paper. It will inform us a lot about what more needs to happen in this space. But again, it's, all emerging research, I would say.
Yeah, and final sort of, it's probably a comment from me. So if you look at most of the models that have been developed by the tech companies, right? So Genome from Google, MatterGen, and there's also one another model from Microsoft. So MatterGen is one. I don't remember the other one. And then if you look at Meta, they have this Harkim group, which most of the data source actually comes from sort of research publications, right? And which are all funded by taxpayer money, one way or another. So either US taxpayer money or Indian taxpayer money, but so they take the data from there, and then they generate models where they don't share the models immediately, right? Because they try to sort of monetize or
they will share a lower version, and
Yeah, exactly. So that's something that I don't fully appreciate from the tech company. It's similar to what OpenAI is doing from the internet at large, right? These companies are doing it for a smaller domain. So if you had some advocacy, please do pass on this feedback from academia that if you take academic data, it's good to share the models, the state of the art with academics.
Absolutely.
So that we can actually contribute and make them better. I mean, it's not like, we don't want you to make money out of it. It's just that we want to work with the state of the art too, and, not be shielded away from this. With that, I would, take questions from the audience. Okay. So one question is, will AI limit the research to the AI models? AI models is knowledge, particularly where you're using to push the frontiers. So basically, if you use AI to generate knowledge for generating AI models, will it be a stunting factor in the development of those models? So basically, use generative models to generate data and then subsequently train advanced versions of your AI models. will that be a
Yes,
stunting factor or an enhancing factor?
that will be a enhancing factor, because what happens is there's a prediction which the model gives, but when you then do an experiment in the lab, you may come with the same result or not. If you come with the same result, then it's validated. If you don't come with the same result, you definitely want to inform the model to learn from that experience. So in that way, it is always enhancing, and that's the loop we should follow. Otherwise, your model will be stale. It is the beauty of why we think agents will be successful is because they have this faculty of interacting with the world and take feedback. If that is not there, then there will be no progress. And then, like compared to humans, why are humans successful? Because we can interact, we have senses, we can talk, we can understand, we can take feedback. We are taking feedback all the time. And that's how you survive in the world. So that will only help us.
So I guess the generated data plus feedback is very important when you improving the models. There's a question from a student, I think. So as a student, I'm stuck between, do I use AI to make my education easier, or do I focus on actually developing on how to do it myself? So he or she says that I'm a person who doesn't want to use AI to do my assignments. But my friend says that if the future is going to be filled with AI, then why not learn to use AI to basically solve his or her assignments?
Okay. Yeah. So I can give you my own personal experience. So because I do coding, right? So now coding, if you see, the most effective agent in the world is a coding agent. That's the one which is most successful. Now, how does that impact me and my colleagues in their jobs? So some of the work, when it comes to basic coding or basic steps that you need to take, the agent is very good, is what my observation is. But when you talk about developing a software architecture or really scaling for performance, or how to support how the UX is interacting with the human, those are the things where a basic coding agent cannot do much. So the idea is that for the basic things, which is, you've got the idea, you've written the algorithm, now you just need to generate something which is few steps. You should go ahead and, use AI, because there'll be a lot of things that you need to focus your thinking, your deep thinking on. It's like in maths, you use a calculator, right? You don't say, oh, I need to learn how to multiply myself because I will not use the calculator. Some point in time, our parents used to say, why are you using calculator? You should know how to do it in your mind. But now we are all using the calculator. It's a general tool available. If you do not use AI in your work, you will lose out, but you will not be able to do everything. There'll be so much more you will still have to do. So go ahead and use it. Of course, if you have to pass your exams and whatnot, you can't cheat and use AI. You have to do it yourself. But it's a great tool. Use it wherever you have an opportunity. That's what I would say.
Okay. Yeah, that's I think good advice. So the student should take it. The next question. So could you please comment on average man hours it takes for an organization or a lab to ingest their data from sort of lab notebooks into the Bodhi platform? Before they can start leveraging the AI-enabled predictivity features. So how long does it take to ingest?
So they can actually start without importing anything. They can just go and do data entry for a particular project or a particular experiment or a particular trial. And they can start from there and build their knowledge base as they go. Or if their data is in tabular form, they can bring that in. If their data is in unstructured form in documents, they can bring that in. So it's like zero time. You can be up. You just need to be on the platform, I would say.
Okay. Yeah. There's one question on for a scientist or a research group in India. What is the accessibility of AI tools like? So can I start using these tools today?
Yes, most of them are in open source. If you go to Hugging Face, if you search for materials and chemistry models, in fact, you'll find the open source page where IBM has their models. You can join like different groups. What the Bodhi scientist platform is trying to do is bring accessibility at a very for India, built in India at a very comfortable price point. So you could register for them, Then you could go to, again, as I said, Meta is open sourcing a lot of things. And then there are, with like you use ChatGPT, there's a pro version and there's a free version. A lot of these tools would be supporting that in future. So it is very much accessible right now here for the whole community.
Yeah. A couple of final questions. So one question is, in the field of biotechnology, will using existing AI be beneficial for research? And an allied question to that is, are there sort of research groups or alliances where you can use computer science and material science tools and frameworks together?
Yes, there are. So I talked to you about, I'll just put this up. So there is this group. Okay, I haven't mentioned it. There's this OMAT, Open Materials. You are using AI and material knowledge together here, or chemistry knowledge together here. Similarly, there could be different areas there is quantum. By the way, quantum chemistry enthusiasts can also work with IBM for quantum machine learning, quantum chemistry. The computers are out there in open. Most of the IITs have some kind of partnership. You can leverage all of that for your research work here and now, like right now, without anybody's permission. So there are so many resources. You can reach out to me as well, and I can help you out in whichever domain you would like.
Okay. And the final question, a little bit philosophical / controversial question. AI cannot make decisions like humans do and cannot follow human emotions like morals, ethics, values, and so on. So how do we rely on AI in the case of conflict management?
Right. So there is again some work which is happening where we are trying to bring digital tools to govern AI, right? For fairness, for trust, for responsibility, for all the human values that we cherish. There is work, and a lot of that work is actually backed here, and it is a different topic. Like there can be a webinar session just on its own, like what are the governance tools, what are the frameworks, how do we embed all these principles when we are designing solutions. But yes, it's very much needed. Some kind of guardrails, controls, and some kind of explainability to the whole thing. Again, it's both research and some of it is there. So, but it's too short to answer the question. But the idea is like IBM is pretty serious about this particular topic, and we have an entire platform on What's the Next Gov that just addresses this kind of a question.
Great. So thanks a lot, Trapti, for the nice talk and for patiently answering all the questions. I think we had a very good, healthy discussion today. AI being a very sort of topic of concern and interest for most people. So I'll like to hand the stage back to Sushila.
Thank you. Thank you very much. Yes, this was a very exciting session and one that we really looked forward to. So thank you, Trapti, for so readily agreeing to do this. And of course, Dr. Sai, thank you for agreeing to be the interlocutor here. Way back in the 90s, we used to be very excited because we were part of cancer drug discovery process. Accelris, now BioVia, used to have a screensaver that we all put on our computers and, distributed processing and so on. And from then to now, what a huge transformation has taken place. And, it's just so much faster. There is so much more excitement, so many more possibilities. So it's a completely different game today in terms of molecule discovery and chemistry and science. Absolutely fascinating what is possible today. We started today by looking at invention and commercialization, what the process is like, how we go from ideas to discover viable materials and then further take them to the market or improving materials as well. And Trapti told us how at every step AI can actually augment the process. She then talked us through the methods from the statistical tools of the 90s to now, as larger data sets have come in. Structured and unstructured data sets need to be analyzed together. Extracting knowledge and not just analyzing data. So that's where the big difference is between what used to be and what is today. She then focused on agents and agentic AI as the latest method. And of course, the appropriate tools that go with it, the kind of complex calculations that are possible. She gave us and walked us through the example of biopolymer design pipeline and the cyclic process of prediction, experiment, design, and back again. She also explained to us about generative AI for material science, how, both understanding data as is, and also how net new generation of structures, molecules, properties, all of that is possible. The couple of other concepts were autoencoders and a mechanism to measure novelty. Then we then spent a lot of time looking at multi-agent reasoning, the roles that agents can assume around the human scientist, and how whether you can look at a structured model with all of that, or let loose the agents and allow them to coordinate, adding, of course, human review as required, and more of that later. Then we talked about the state of the art, what is happening, what is going on, how AI has helped both identify many more materials, I think 44% more when you use tools, and also how it has helped generate many more patterns and so on. But the very interesting part of the discussion was how AI in research has actually led to much lower job satisfaction. So that's something we need to think about. We then saw a live demo of Sarthak AI's both scientific and, of course, a lot of details about designing cognitive AI agents for scientific reasoning and planning, and how all of that works. It was an absolutely fascinating discussion around reasoning modules, reasoning procedures, and how they are designed to use the three different types of memory that we take for granted. And lastly, what exists: open source tools, closed source tools. But again, an interesting takeaway was we are seeing industry transformation. We are seeing a lot of cross-industry, the borders between industries kind of blurring. And especially, we used to say that technology companies are not just technology, but process and so on. But today, what we are seeing is tech companies are becoming chemistry companies, materials companies. And very interesting, when you talked about Meta's intelligent glasses, one really wonders how you classify companies and industries in today's world. But the good thing is, of course, that they've put it in the open source. Really happy about that. And I'm sure Sai is extremely happy about it too. We ended the session with looking at challenges around data diversity, denoising, looking at synthetic data generation, closed loop labs with IoT, and there are a lot of new areas, which is inspiring. And we hope that there will be a lot of people, a lot of students, a lot of professionals who will stay back in science and tech and really, come into taking up a lot of this wonderful, challenging work. And then, so this is again another example of working cross-discipline. Over the 4 years that we've been doing these webinars, one of the themes that we've seen repeatedly is the whole idea of cross-industry collaboration, and why the work that is happening in future, whether in science or in industry, is all about cross-disciplinary work. So we just saw a lot of that today as well. And then, it was also very nice to hear that there are tools being created to govern AI, so self-governing in another way. And yes, the offer to do another webinar, completely just tell us when. We'll be very happy to host one. So, while we saw all of this today, I want to end with a reminder for all of us, and that comes from Ginny Rometty, former executive chair of IBM. She said that the key to success with AI is not just having the right data, but also asking the right questions. So we are very much at the center of it all. Let's not assume that AI will take over the world. So thank you very much for being part of this webinar. Thank you for all the fascinating insights. And our audience, of course, thank you for being here and for your questions. We hope you will enjoy working with AI and speeding up your research. So thank you again, and look forward to seeing you at our next webinar.
Thank you. Thank you for having me. Bye.
Bye.
See you.
Thank you.